is x to the n plus 1 over n plus 1 plus a constant c. Alright, so when I take the integral of 2x, the 2 will come across the integral sign, and we'll pull that out later. We'll leave it right in front, but then we integrate x dx. Following this form, x is to the 1. I increase it by 1 and divide by that new number, and then it's that. Plus c. Alright, so we end up with x squared plus c. And that is to be evaluated at minus 2 and 1. Fundamental theorem says to put the 1 in the upper limit of integration in, and then subtract the lower limit of integration, substitute it in. So watch what happens when I put in a 1. I get 1 squared plus c, then a minus sign. Now I'm going to put in a negative 2, which is squared plus c. Notice I get a 1 plus c and a minus. This is a positive 4, and the minus in front makes it negative, and then this minus makes the c negative. That c cancels out that c, and it will always do that. So when we take a definite integral like this, we do not even mess with the plus c, because we know when we take the upper limit of integration and subtract the lower, the c's will always cancel out. So I wanted to take a moment and show you why the c's sort of disappeared when we did integration. That's why. So the c's are gone, and we just end up with a 1 squared. So we're over here. So I get a 1 squared minus a negative 2 squared, 1 minus 4, which is minus 3. Okay, in a graphing form, let's see what's happening. We have the function y equals 2x. That was our original problem. Y equals 2x. So I can graph that. It crosses the x-axis and the y-axis. It crosses the y-axis at the origin and has a slope with a rise of 2 and a run of 1. So it's a steep line like that. And we're looking at that value, the difference between that function and the x-axis between negative 2 and 1. Negative 2 and 1. So this is what we see. So what the integral does, it takes any area above the x-axis and calculates it as positive, and takes area below the x-axis and calculates it as negative. So you can see from our picture there's more negative area than positive, thus that's why we have a negative answer. And we'll get more into positive and negative. We'll talk about area again. So it's not truly an area anymore if we call it a negative value, but the integral will take the area under here and assign it a negative value and this a positive value. So I want you to be aware what the integral is doing. Alright. So we're happy now, including negative answers to our integration problems. We'll finish tonight by looking at some properties of definite integrals. Again, this is not a property of a definite integral. It's the fundamental theorem of calculus. So just recalling, that's how capital F stands for the integral. So I've taken the integral of this function, substituted in b, and subtracted the integral of this function, substituting in a. Alright, so we're getting comfortable with that and using it a lot. Alright, the properties, I think there are 5 properties I want to go over, and several of them you've already seen. So the first one, let's look at the integral from a to b, and I'm going to draw a picture as if this function is positive, but all these outcomes will work if the integral turns out to be negative. So let's say we have some constant times a function. So I've drawn a picture here. Here is the integral from a to b and the function f. But if I multiply that function by numbers, say like 3, so I multiply it by 2 and then by 3, so this looks like a 3 times the original function. So let's talk about what that will do to the area between the original function. There's that, but look at the area under the tripled function. It looks like it's 3 times as much as the area under the original function. So it's no stretch for you to see that that k can come across the integral sign and not be affecting it, and just find the integral of f of x from a to b. Alright, and that is a principle, and we've already used that, so I just wanted to show you a little more about why it's true. Alright, then we'll go to the next one. We're going to take an integral of one function, add it to another function behind the integral sign. So let's look at a picture of what that leads to. So if this is function a to b, so we're looking at this area under the curve for f of x, and if we add g of x to f of x, what would that look like? Well, here's f of x, and it's that far from the x-axis, but g of x is that far. So if I added the two, I'm going to have to add this to f. So it's going to bring us up here somewhere. So this would be f of x plus g of x. So the area from that curve to the x-axis would look like that. Can you see that I could also think of it as this area plus this area? Am I getting too many lines in there? So this area under this curve plus this area under this curve should equal the area under the sum of the two curves. So that means we can split this into two individual integrals. And I forget my dx sometimes. And we have done that already. So the integral of a sum is the sum of the integrals. So that also works with a minus sign. The picture doesn't show that, but it does work. All right, the next property, let's see, how long have I been chatting here? All right, probably too long. So I'm going to shut this down and start the next part.